Alright guys, by the time you're done with this video you should be able to know what force is, and you should be able to understand the different kinds of forces. We can talk about balanced versus unbalanced forces, and then something called net force. Both of these two things work together to determine how forces impact how objects move. So that's the goal. Let's get to it. Now, a force is just a push or a pull on an object. Now, you guys know a lot about forces, and if you're a sibling, you have brothers or sisters, you've seen pushes or pulls before. They're easy. Sometimes forces are really easy to see. However, there are other times when it's not so obvious when a force is acting on an object. Sometimes the force seems invisible. Now, the invisible force that I'm kind of talking about would be, the force due to gravity. It's hard to actually see gravity working on you when you're not doing a whole lot. However, gravity can also be very obvious. When you throw something up into the air, it will fall down. Now, kind of keep that in mind. Sometimes forces are easy to see, sometimes they're not. What we're going to do next is talk about forces, different kinds, and we're going to start talking about forces that act when two objects are in contact with one another. So these are the contact forces. Now, these ones should be all pretty familiar to you. You got the force of friction. Now, friction, what it does is it opposes motion. That's its goal. That's what it wants to do. So anytime you have two things or anytime you have something that's moving, there's going to be some sort of frictional force, whether the object is running, the object is sliding. Anytime it's moving, it's going to be having some sort of friction. So if the object is moving to the right, there's going to be a frictional force, F, frictional force opposing that motion. Now, tension forces, one of those forces that's kind of hard to see, but it's something that you can definitely feel. I like to shorten this thing up to F sub T, force due to tension. Usually that's going to be in the rope, string, cable. Great way to remember tension force is fun game, tug of war. You really can't see the force in the rope, but if you're playing the tug of war, if you actually touch the rope when they're playing, you can definitely feel that tension force. And then we have force due to air resistance. Now this is a frictional force, so this guy goes back up here. Anytime you have an object moving in air, you're going to have a frictional force, and that's going to be the force of air resistance. So anytime you throw something through the air or you're falling through the air, there's going to be some sort of air resistance force opposing that motion. So if you have an object falling down, you're going to have force of air resistance going up. Now the next one is kind of strange to think about, but it's really, really important. It's this guy right here, the normal force. And you can definitely think of it as a support force when two objects are in contact with one another. And usually one of those objects has to be stable. So what I mean by that is, you've got a table, and on that table you have a box. Now, the force that's holding that box to the table is the force of gravity down. Now, if that was the only force acting on the box would get smushed. Okay. However, box doesn't do that. The box doesn't fall through the table. What it does is it just stays there and does nothing. And the reason why it does nothing and doesn't get smushed is because there's actually a force going up that's equal and opposite to the force of gravity, and that is my Fn, my normal force. Okay, so when you're sitting in a chair, you have the force of gravity pushing you down, and then there's also a normal force from the chair pushing up on your body as well. Okay, so that's the normal force. Has to be when you have two objects in contact, and one of those objects is pretty stable. Now the Fa, the applied force, pretty obvious. Okay, just think of big brother, big sister pushing. Okay, you're applying a force to an object. All right, if you're taking notes right now, you're applying a force to your pen or pencil. All right, and then the last one, Fs, is the spring force. Okay, spring force, is going to be in any type of spring. If you played with springs before and you squish them or you pull them, you kind of feel that spring pushing or pulling against you. Okay, that's because the spring itself has spring force inside of it. Okay, now all of those forces had to be in contact with one another, but there are a lot of other forces that don't actually need to be in contact. Okay, perfect example is this guy right here, force of gravity, F, G, force of gravity. You can have two objects. We can kind of think of planets. Okay, we got, the sun here, big, huge, gigantic object, and then you've got the Earth over here. They're not in contact with one another, but there is a force of gravity, force of attraction between those two objects, F, G, both of them. And that force of gravity kind of keeps the Earth doing its orbit around the sun. Okay, not in contact, but the force of gravity is still there. And you've seen that with this guy right here, force of or the magnetic force. Okay, the magnets that you're playing with don't actually have to be in contact with one another for you to actually feel the force between the two of them. Okay, now those are all the different kinds of forces that we're going to be talking about in this class. There are many other types, but what we're going to do now is talk a little bit more about something called net force. Okay, but before we get there, we need to realize that a force can cause an object to change its motion. This guy right here, change motion. That should kind of spark something in your mind, something called acceleration. Okay, so without a force, acceleration doesn't happen. Okay, now with a force, does acceleration happen? Well, we have to look at this word right here, can. All right, so just because you have a force doesn't mean that you're automatically going to accelerate an object. I mean, you can push against the wall all you want, but the wall is going to be stronger than you. So the force that you're applying doesn't cause the wall to accelerate. Okay, you have to have something called an unbalanced force to get an object to accelerate. So let's talk a little bit more about this idea called net force. Now, when we're talking about forces is something that we can measure, and we measure that in something called newtons. I would just, whenever I'm doing a math problem, I would just use this guy right here, this capital N for my symbol for newtons. I wouldn't write the whole thing out. Now, what we can do is we can actually figure out all of the forces acting on an object. So what I might do is I might use this symbol right here, sigma. Okay, and sigma just means sum, not S-O-M-E, S-U-M. Okay, so the sum of 2 and 2, sum is figuring out the total, sum is 4. All right, so what I might do is I might give you this right here in a math problem, find sigma F. Okay, when I do that, I'm asking you to figure out the sum of all of the forces acting on the object. Now, here's where the tricky part comes in. Sum, in this case, meant to add, right? But in some cases, we might need to add or subtract. Okay, and it just kind of depends on the forces themselves. So let's get into that a little bit. Now, if I take a look at these guys in this picture, this team working hard together to try and beat this team over here. So if I wanted to figure out the net force or the sum of the forces of these guys, all I would have to do is add up all of the forces of these guys, right? That would be the force, the total force of all these guys. I'd do the same thing for these guys over here. I would add up all of their forces to try and figure out their net force, right? But now, what if I wanted to try and figure out the net force on the rope? This one gets a little bit tricky, right? Because I have these guys pulling this way, and I have these guys pulling this way. So what I would do is I would take all of these forces, add them all together, and I would subtract them from all of these forces, okay, because they're going in opposite directions. All right, so let's write this stuff down. Sum total of all the forces, from now on I'm just going to call that the net force. All right, now if all the forces are working together, working in the same direction, this is key here, guys. If they're working in the same direction, I'm going to add all of those together. However, if forces are working against each other, like in this tug of war example, they're going in opposite directions, I'm going to subtract them. Okay, really, really important. Going in the same direction, you add them. Going in opposite directions, you subtract them. Now, this is going to be really important when we start talking about if objects are going to accelerate or not. So, in the case of balanced forces, all right, so we have one force here, we have another force right here. What you notice about the direction of the arrows? Well, they're going in opposite directions. That's why we're subtracting them. Okay, they are equal in length. Okay, so they're equal in magnitude. All right, so if I take one, subtract it from the other, I'm going to get 0 net force. Okay, 0 net force. Does that mean that there aren't any forces acting on this object? No, I have 2 forces acting on this object. The thing is, they're going in opposite directions. Okay, whenever the net force is equal to 0, I would highlight, star, underline this part right here. There is no change in the object's motion, or there's no change in velocity. What that means is that you do not get any acceleration. The object is just going to keep doing what it's always been doing. So if you think about it, if the object is moving and the net force is 0, what is the object going to continue to do? Since there's no change in motion, it will continue to move. Don't get that messed up. Just because the net force is 0 does not mean that the object is stationary. It's not moving. It could be. Okay, but if the object is not moving and the net force is 0, then it's going to continue to not move. All right. Okay. It might be sounding like I'm preaching to you guys, but this is really, really important. So let's talk about unbalanced forces now. What that means is when you add up all the forces, your net force is not going to be 0. Not 0. All right, so you're going to get some sort of number. Okay, and that's good. Okay, because what that's going to do, again, highlight, underline, star this thing, is going to cause a change in motion. And again, right here, change in motion means acceleration. All right, so whenever you have a net force that is not 0, your object is going to accelerate. All right, and that's how we get objects to change their motion. All right, guys. So that is my spiel for forces, unbalanced, net force, balanced, and how they impact forces motion, or the motion of an object. Make sure you watch this as many times as you can.